Okay, yeah, see you in a bit. Good morning. Okay, just to remind you, we last week we actually, because we finished the previous lecture sheet early, so we carried on with this one. So we got a couple of 2 or 3 slides into this. Hence, there were a few copies which hadn't been picked up last week, and in addition there was the lecture which follows and a problem sheet. So I hope you can make sense of all of that. Right, so let me just remind you what we had started on. We had gone back to the idea of a system of particles, which is something which you already encountered, I hope, in Michaelmas term. And we warmed up by deriving results which you probably should have seen before, which showed that for our system of particles, we start obviously just considering 2 particles. We saw that, for example, we were able to write, this was from last week, that the total mass of the system multiplied by the acceleration of the center of mass is equal to the sum over the external forces. Okay? So the whole system can be represented by a single particle accelerating where the center of mass is accelerating, and it's driven by the external forces. Also, this is at the bottom of this slide, that the kinetic energy T is equal to what I call T prime, which is the kinetic energy in the lab, plus the kinetic energy of the moving center of mass. Okay, so again, this is M total. So those are results for translational motion, but they were revision to get us warmed up for looking at rotational motion. So that is where we start today. Okay, so things which...
Is that the kinetic energy in the center of mass?
When I wrote lab, that's a good way to start, isn't it? Lab obviously means in the center of mass. I don't even know why I did that. This is it. This is in lab. That doesn't bode well, does it? Hang on. I blame it on the previous lecturer. He didn't get out in time. So sorry about who was that? Oh, sorry, I undershot. Right, let me try and concentrate more. Right. Okay, so back to now to rotational motion. This is the definition of angular momentum. This is the definition of torque. Okay, so for a system of particles, we can just make a linear sum. So for a system of particles, therefore the J dot for the system is going to be the sum over all the torques, right? Now those torques, what forces are acting on this system? There are, as in the consideration for this, there are external forces and there are internal forces, external and internal. So there's contributions from external and internal torques. So what I think you might guess what might happen. Let's just consider the internal contribution. So these operate between pairs of particles. So in principle, the force coming from this particle M1 acting on M2, or Mi acting on Mj, will exert a force. So, and then the other particle will exert a force and a torque backwards. So we need to consider pairs of particles. Okay, so this is a sum over all pairs, and so I designate that torque Ij. So this is between particle I and the particle J. And so you get Ri cross F internal Ij, and then you get a Rj cross F internal Ji. Okay. But we have, of course, Newton 3, which tells us that Fij internal is equal to minus Fji internal. And so this sum, if I can just write it like that, if you'll let me, can be represented as Ri minus Rj cross Fij internal. Okay, so that's, so now we look at this, and Ri minus Rj, so this is Ri, this is, and then we can substitute minus Rj, and we get a vector which is going directly from Mi to Mj. Okay, Ri minus Rj gives you a vector from Mi to Mj, and that vector is entirely parallel and indeed coincident with the line of force between the two particles. So this is 0, since Ri minus Rj is parallel to Fij int. So we deduce from that that all the internal torques will cancel, and so J dot will just be a sum over the external torques. Okay. So that is so the rate of change of angular momentum is the sum over the external torques. That's very reminiscent of that the rate of change of momentum of a system will be the sum over the external forces. So this is a direct rotational analogue of something you know well from the linear case. And one consequence is that if there are no external torques, then J dot equals 0, and so that J equals constant if no external torques. Okay, let's now look at one other thing. Let's consider the angular momentum itself in a little more detail. So the angular momentum is expressed in the lab frame. Well, this J, let us say, is in lab frame. So let us again see if we can decompose this into quantities within the centre of mass and referring to the centre of mass as evaluated in the lab frame. So to go from the lab to the CM, we have these translations which we've used already. So Ri, that's in the lab, Ri prime, that's in the centre of mass, and Rcm is the position vector of the centre of mass. So just to be clear, that's lab, and that is a centre of mass. I get it right this time. And also we have the velocity vector Vi equals Vi prime plus V centre of mass. So what is the total angular momentum of the system? So J will be the sum over all the contributing J's for up to n particles, and we therefore can substitute, well, Ji is Ri cross Pi, so just substituting this in, we get Mi Ri prime plus R centre of mass crossed with Vi prime plus V centre of mass. Okay, so that's just that Ri cross Pi with this translation substituted in. So let's evaluate this. We're going to get 4 terms. The first term, Mi, this with this, I prime cross V I prime. Write it underneath. Then the next contribution is Mi Ri prime cross VCM. So that's this with this. And then Mi RCM cross VI prime. And finally, Mi RCM cross VCM. Okay, so 4 contributions. Now, 2 of these contributions vanish. Which ones are they? They are this one and this one. Why is that so? It's because it's all to do with the definition of the centre of mass frame. The first one vanishes because the sum over Mi Ri prime equals 0. So when you're so these are the position vectors in the centre of mass. If you weight those, so by the definition of the centre of mass, that goes. Also, we know the centre of mass frame is the 0 momentum frame, and that explains this second term which vanishes, because Mi Vi prime equals 0, because we're in the 0 momentum frame. Okay, so we're left with just 2 terms, and the first term involves R prime and V prime, so I can write that as J prime, so that's angular momentum in the centre of mass, and the other term which remains just involves the centre of mass coordinates, so this is plus RCM cross big M VCM. So this is the angular momentum of the centre of mass. Okay. Which is, again, what we have written here. So once more, things decompose very neatly. The total angular momentum in the lab can be written as the angular momentum of the centre of mass in the lab frame, that's what I mean by this, plus the angular momentum of the particles with respect to each other in the centre of mass. Okay, so what have we learnt? I'm just ramming it home now. Newton's laws relate to rotating systems in the same way that the laws relate to translational motion. For any system of particles, the rate of change of angular momentum about an origin is equal to the total torque of the external forces about the origin. And finally, as we've seen here, the total angular momentum about an origin is the sum of the total angular momentum of particles about the centre of mass plus the angular momentum of the centre of mass in the lab frame. Right, let us now move on to a moment of inertia. So this has been introduced for a single, we did introduce this briefly, so moment of inertia for a single particle. Just if you want to look back, this was introduced in lecture 14. But now we're going to consider the angular momentum of a system of particles, starting with, as ever, just two masses. And what we're going to do, we're going to, so these systems will be rotating. So we have an axis, we have, and there'll be a rotation with an angular velocity omega. And initially we will have the particles in a plane such that the normal of that plane is coincident with the axis of rotation. Okay, so we're going to consider successively different configurations of these system of particles and then try and draw some general lessons from it. Okay, so the total angular momentum will just be R1 cross P1, which is M1 V1, plus R2 cross P2, which is M2 V2. But we have expressions for V1 and V2, so V1 is equal to omega cross R1, and V2 is omega cross R2. Okay, so we now have if we substitute this in, we have a triple cross product, and so we reach for our sheet of vector identities. So we're just going to use that A cross B cross C is the same as A dot C multiplied by B minus A dot B multiplied by C. Okay, so in this case, so we have a R cross omega cross R, and that's going to be equal to, by this identity, R squared omega minus R dot omega R. Now, because the way we've set up the problem, R dot omega is 0 because R, so this is a plane, as I say, and we put this plane, so it's so the vector pointing out to this plane is parallel to the omega vector. So in other words, R is perpendicular to omega. So this goes since R is perpendicular to omega. And hence, we just then end up with that J, we just have contributions from this first term, but we have it for the two particles. So we have M1 R1 squared plus M2 R2 squared omega. So the angular momentum is equal to something times the angular velocity, and that's something which has the role of has the same role as mass, but for rotational motion. We call this the this is I, which is the moment of inertia. So back on in lecture 14, we briefly saw that and defined it for a single particle. It's mass times distance squared, roughly. Now we have it for two particles. So in general, therefore, I is equal to the sum over mi times ri squared, should we have more than two particles in the game. Okay, so this is one system. Let's now consider a slightly more complicated system where now these two masses, you imagine them connected by a rod. One important consideration in everything we'll be saying is that the system is rigid, so we're not allowing for any movement between the two. But now let's imagine that this rod is tilted. So again, this is the axis around which the rotation happens, but the system is clearly somewhat more complicated. So J, we know J is perpendicular to both R and the velocity. So J is pointing along what I call the Z prime axis. So J is along Z prime, which is not clearly the same as Z. Okay. And just to introduce a piece of jargon which we'll come to soon, that actually defines what we call the principal axis of the moment of inertia. And we'll talk more about that rather soon. So that is the actual direction of J. Let's calculate the magnitude. So let's do this. So we have we're going to need the magnet. So V, despite this being tilted, V is still perpendicular to R1. So we just need to multiply the magnitudes together. What is the magnitude of V? V1 is equal to D1 times omega, where D is this distance here. And also it's going to be convenient and necessary to bring this angle phi into the game, which is the angle of the tilt. And one sees that geometrically there's a relation between R1, D1 and phi, which is that R1 is equal to D1 over sine phi. And similarly, V2 is equal to D2 omega, and R2 is equal to D2 over sine phi. Okay. So, angular momentum, we need to multiply indeed we need to as previously, therefore that J is equal to the magnitude of J is therefore equal to M1 D1 squared plus M2 D2 squared, all multiplied by omega. It has this sine phi on the bottom, right? Because what I've done is, this is, so J is R1 cross V1, and I've substituted in for V1 and I've substituted in for R1 and R2, hence we have it expressed in terms of D1 and D2 with sine phi on the bottom. Okay? So that's the magnitude of J. And J, to reiterate, is pointing in this direction. But since it's a vector, we can imagine resolving it along the z-axis. So let us resolve along z-axis, and we see that Jz is going to be J times sine phi, which is going to be given by just m1 d1 squared plus m2 d2 squared omega. So this, what have I done now? Oh, you're worried about this to be whether it should be a sine squared. Oh. Just a minute. No, what have I done here? What have I done here? M1. No. For once, I think I'm right. Because, let me. Sorry, because we have J is equal to R cross P, and they're at right angles. So the magnitude is R, well, M R V, and so the V brings in a D1 omega, and the R brings a D1 over sine phi. So we get to D squared, but only 1 sine phi. Okay, sorry if, Now, as I was writing it down, you might have, I was sort of hesitating because something looked odd to me, but it's right. But I fear my hesitancy maybe was translated to you. But we're good, I think. So what we now have done is resolved J along the z-axis. And so now, because we're talking about a particular axis, we can write this as a particular moment of inertia, the moment of inertia in the z direction. So here, Iz, so this is calculated about the z-axis. Okay, so what the message I want to start to convey is that the moment of inertia, it's not just a single quantity for a body, but it takes on different values depending which axis you evaluate it around. Okay, and you may already have some sense of that if you do imagine, if one imagines some dumbbell, two big masses on the end, the actual effort to swing it around over your head will be significant. But if you want to just rotate it around the axis, sorry, we should have really brought in some prop to demonstrate what I mean, but that would be significantly more easy. So again, this thing which is somehow representing mass or rotational motion, it has a different value depending on the axis one evaluates it around. Okay, so now let's go to a still more elaborate system. So now we have not just one particle, but a bunch of particles. Again, they're sort of, you imagine rigid rods connecting them so they don't move with respect to each other. But these masses are now not distributed in a plane, right? So they're scattered over some volume. But again, we have a z-axis which defines the axis of rotation of the system. And this is my origin, which happens to be on that axis. So let's work out the angular momentum in this case. So then J will be the sum over all the particles of Ri cross Mi Vi, which is going to be the sum over M, I, R, I, V, I, and each particle will have associated with it the angular momentum contribution associated with each particle will have a unit vector associated with it, which is the one at right angles to Ri and Vi, which I designate Ui hat. So to be clear, so for this particle here, when I cross Ri and Vi, they're certainly at right angles to each other, but I get a direction associated with that resulting vector, which is right angles to both, which is the direction of this blue vector. But the direction of the blue vector will be different depending on which particle we are making the calculation for. Okay, so let us initially, again, calculate the contribution resolved along the z-axis. After doing that, we'll come back and write a more general expression. So calculate Jz, i.e. Resolved about axis of rotation. Okay. Then we have a Jz in the z direction, and that's going to be, well, it's going to be this sum, but for each contribution we're going to pick out a sine of this angle phi I. So M I R I V I sine phi I. And then this is in the z direction, where we multiply by omega, and I can write omega as a vector because omega is pointing in the z direction. So the sine phi comes from resolving this along this axis. So since phi is defined here, then this is phi. So resolving along this axis gives us a sine. Okay. All right, well, what else? Let's just look at this expression. So M I R I V I sine phi I. How else can we write this? Well, I can write it as M I R I. I write Vi as omega times the di. All right. So this is just representing the velocity v in terms of the distance di and the angular velocity omega. And we also, we can represent phi I in terms of distances. So I can replace this sine phi by something. Let me just write it, then I'll say it. Omega di. Sine phi is nothing more than di over Ri. Okay, because that's what sine phi is. And so we're left with Mi, these Ri's cancel, di squared omega, right? Hence, Jz omega hat is the same as the sum over Mi di squared times omega. So this is Iz, which is the same result we had for this previous case. So same as for previous case. Okay. So we see that the moment of inertia seems to be, resolved so in words, the moment of inertia resolved about this particular axis is the perpendicular distance of each mass from that axis squared multiplied by the mass of that particle, and then we sum over them. So we've been dealing here with a discrete body, so something made up of blobs of masses. We now can generalize to a continuous body. So we go from a discrete to a continuous rigid body, but it is rigid again, so it's not able to deform. So in this case, the sums will just become integrals, but it's going to be convenient and necessary to integrate over a volume. So to integrate over a volume, we need to know a density. So we can express dm as rho dv, and this is the density. And so this Iz, which we have seen for the discrete case, is the sum over mi di squared. That will become an integral over a volume of d squared, where d is the distance from the axis, the perpendicular distance to this element of mass, times rho times dv. Okay, so that sort of is our blueprint for evaluating the moment of inertia for a continuous body, and we will get some practice in doing just that rather shortly. But before doing so, I want to move to this lecture 22, where we will just spend some time talking a little more generally, and we'll introduce something which will initially sound a bit scary, but it's good you know about it. But then we will retreat into simpler calculations involving just this one principle. So what I want to do is, this is just the same. Hello? You're looking for, oh, okay. 22. Yeah. Where did they go? Okay. So, yeah, they seem to have gone like hotcakes. This is just the same issue that we've been looking at, right? So this is just the same thing which we worked out the z component of the angular momentum for. I just want to now work out an expression for the complete angular momentum. So this is the same distributed system. So and let's work out J, not just JZ. Okay, that's what we're doing. So J is going to be given by, so again we're back to this rigid discrete body. So it's a finite sum over Ri cross Pi, which is Ri cross M, writing this as V, which we can write as omega cross Ri. So again we have this vector triple product, so we make use of the identity which we make use of this identity. So using vector triple cross product, then we get J is equal to the sum over MIRI squared omega minus the sum over MIRI dot omega RI. So this is what we already more or less wrote down, but in the case where we wrote it down when the two particles were in a plane, where the plane was had a vector which was parallel to the z-axis. So in that case it vanished, but in this case that won't vanish because R and omega in general are not at right angles. So this in general does not vanish, unlike earlier case. Okay. So yes, this was the earlier case, the circular motion in the plane. So this is a more complete expression. So this is a vector, and it has 3 components. Let us try and write out one of them. One will be quite enough. So let's write out Jx, okay? So I have Jx. So firstly, this case here, so we're going to Ri squared, well, so it's the sum over Mi, and Ri squared can be written as xi squared plus yi squared plus zi squared multiplied by, and let's keep it completely general, so let us, omega will allow it to point in any direction, so it can in principle have an x component, and we're evaluating the x component. So omega x, and then we have this contribution here, so this is minus the sum over mi, and then we have to evaluate Ri dot omega, so that's going to be xi omega x plus yi omega y plus zi omega z. And again, Ri, that's a vector, and we're evaluating x components, so we get xi. Okay, now we look at that for a bit. So you have xi squared. All of this is multiplied by xi, so we've got an xi squared there also, but this has got a minus sign in front. So this cancels. And so we're left with that first term, just writing this out, is therefore mi times yi squared plus zi squared omega x minus mi x I y I omega y. So that's this term. And then we're going to have a minus mi x I z I omega z. Okay. And I said that's quite enough, so let's just say similarly for jy and jz. So these are slightly non-trivial expressions, but they can be written in a compact way. So nothing known. So what? So you see that this expression for j here involves both contributions linear in omega x, in omega y, and in omega z. So it's a linear expression, so we can construct a matrix equation, okay? And so I've done this for you, one here prepared earlier. So this, just in your mind, if you look at this top line here, if you multiply this by this, you will get this expression, okay? And this is for the rigid body. If we wanted to make the body continuous, then everything would look the same, but these would become integrals. But we can represent, so this quantity here in the middle, it's not a number, it's a matrix, and moreover, we write it, we say it's a tensor. So sometimes we represent a tensor with a twiddle on the top. So this is the moment of inertia tensor. So tensors sound nasty and forbidding things. They play a big role in general relativity. But all this is doing is, the point is that this matrix enables the direction of the angular momentum to be different from the direction of the actual angular velocity, okay? So as well as giving a factor, it's also in general rotating this vector with respect to this vector. So let's talk a little bit more. So I've rewritten this moment of inertia tensor in these terms. Now here's a wonderful thing happens, because you can actually, the form this matrix will take depends on your coordinate system, naturally, okay? So each element will have a particular value which is contingent and dependent on the coordinate system you are using. Now it is possible, and this is something we're not going to prove, I'm just going to, one of the wonderful phrases in physics, it is possible to actually choose a coordinate system such that the tensor matrix diagonalizes, okay? And the axes of that coordinate system are called the principal axes. And if you have a body which has obvious axes of symmetry, then those axes of symmetry will be the principal axes. And the diagonal terms are called the principal moments of inertia. Okay, so in this case, then, rather than having this horrible matrix, you just have three quantities, one quantity corresponding to each axis you are considering. So then J will be equal to, for instance, I double X multiplied by this. And through laziness, we often drop this second subscript. So instead of writing I double Z, we would write IZ. And that's what we have been doing until now. Okay. So this is, just to tell you about this greater truth, this more complicated and complete vision of how moments of inertia work. But from now on, and I think it's true to say in prelims questions, we will just be dealing with moments of inertia, what we call the principal moments of inertia, which are one of these three quantities. So a moment of inertia evaluated around a single axis. And that is much cuddlier and easier to maybe deal with than in the case of than dealing with a full-blown tensor. Okay, so finally, and very finally, I want to talk about moments of inertia and energy of rotation. So again, this is our general spinning body. Let us work out what the kinetic energy is. P is a half sum over mi vi squared, which we can write as a half mi omega cross ri all squared. But again, we have a nice vector identity, which is that A cross B all squared can be written as A squared B squared minus A dot B all squared. Okay. So making use of this, we can say that T is a half mi omega squared I squared minus mi omega dot I squared. Now you might say, well, that doesn't look an improvement, but it's a very useful expression, because if I go back to 2 slides previously, you see that that is exactly the same as what we have here. So we can write just with an extra omega in the game. So this can be written as a half j dot omega. I'm making use of a previous expression for j. Okay, so T is equal to a half j dot omega, or if I substitute in what we know j to be in terms of the moment of inertia, that's a half I tilde, this is what we call it, omega dot omega. So this is making use of the full moment of inertia tensor. Or if in the case we are the axis of rotation is one of the principal axes, so in case Z is a principal axis, and Z is important because omega is in that direction, then this simplifies to a half I Z omega squared. Okay, so this is the expression for the angular, the kinetic energy of a rotating system. It's essentially, so if we're rotating around the z-axis, then it's just a half times the moment of inertia about that axis times omega squared. So very, very reminiscent of a half mv squared, but this is the rotational analog. Okay, so let us stop there, and tomorrow we will now calculate the moment of inertia for various simple systems.